Hi, I am Raghavan, Chemistry Faculty from Alfords College. I invite you all for the Alfords Chemistry e-learning classes. Today, session 33rd. Okay. In the last session, 32nd, we have done off-bow principle, that is Euler's diagram we completed. So that is energy levels of the orbitals and how to discriminate the energies of the that is orbitals, atomic orbitals, and we explained the off-bow principles based on the n plus L values. Okay, so now let us practice 2-3 examples, that is how to write the examples, how to write electron configuration, okay, based on the off-bow principle. Okay, let us take first element, the element with atomic number. Say atomic number is 7, atomic number 7. Okay, so that electrons, that is first 1s2, then next electrons goes into 2s2 according to the off-bow principle, that is Euler's diagram only we are moving. Okay, so 1s2, 2s2, the next 2p3. Okay, the remaining 3 electrons goes into p sub shell because so p orbitals can accommodate maximum 1 to 6 electrons. Okay, next one more element, that is atomic number 34. Let us take up 34. Okay, now we have got 34 electrons. We have to distribute among the molecule, that is atomic orbitals. Okay, according to the off-bow principle. Just you have to follow only the according to the off-bow principle. You have to distribute the maximum capacity of the electron among the atomic orbitals according to the off-bow principle. Okay, that should not forget. Okay, first, so it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2, 3d10. Okay, up to this how many electrons completed? 10, 20, 30 electrons are completed. Okay, next 4p orbital is filled with the remaining balance 4 electrons. Okay, that is the way to write the electron configuration of elements according to the Euler's diagram of off-bow principle. Okay, is it clear to all of you? Okay, once again let us take another one. Let us take the big one. The element with atomic number 86. 86. Okay, so that is 86. Let us write the configuration of all these electrons. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, you should read that is along with me you have to read the configuration according to the off-bow principle. That is, it is nothing but only the for practice I am giving. Okay, 3p6, then 4s2, then 3d10, then 4p6, 4p6, then 5s2, next 4d10. After that, the next electrons goes into 5p orbital, 5p6. Okay, 5p6. After that is 5 periods are completed. The next electrons goes into 6s2. After 6s2, the next orbital is 4f orbital. Okay, 4f14. Because f orbital can accommodate maximum up to 14 electrons. Okay, then 5d10. Okay, as per the off-bow principle, that is Euler's diagram. 6s2, 4f14, 5d10 and 6p6. 6p6. So this is a way to write the electron configuration of elements. Okay, just we have to proceed according to the off-bow principle. That is importance of this off-bow principle. Okay, Euler's diagram of off-bow principle. So like this we can write the electron configuration of elements. Okay, you can write electron configurations like this. Right. So the next is Hund's rule of maximum multiplicity. Okay, the next concept in the electron configuration is Hund's rule. Okay, off-bow principle is completed. So once again, what is the basic fundamental of off-bow principle? What idea it gives us? So off-bow principle explains that how the electron enter in which orbital. How the electron enter in which orbital. Okay, electron always enters into the atomic orbital having least energy. That is the main idea, main concept of this. Okay, that is, see, among all the atomic orbitals, we have bunch of atomic orbitals. Among all the atomic orbitals, the orbital with least energy, first electron goes into that. Okay, so that is according to the Aufbau principle. It states that electron enters into the atomic orbital having least energy. That is the point. Okay, so that is the building up of electrons, among the atomic orbitals are in the increasing order of their energies. See, for example, when we are going to the 10 floors building, we have, okay, 10 floors. Now we are in the normal ground state. Okay, so how we are going? So first we will go first floor, second floor, third floor, fourth floor, like that. That is slowly in the increasing order. Similarly, the electron also occupies the lowest energy atomic orbitals first, then highest energy, then higher energy, then higher energy. It goes like that, right? So now next concept is Hund's rule of maximum multiplicity. Yes, that is the second fundamental of electron configuration, that is Hund's rule of maximum multiplicity. 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 It explains that Hund's rule of maximum multiplicity, it explains that how the electron pairing takes place. It explains pairing of electrons. Okay, so how the electron pairing takes place in the atomic orbitals. Yes, so it explains pairing of electrons. It explains pairing of electron. Okay, pairing of electrons. It explains pairing of electrons. So according to Hund's rule, pairing of electron takes place. Pairing of electron takes place when after all the degenerated orbitals filled with one electron each of parallel spin. Okay, you got it? So once again, so what are degenerated orbitals? So that is equal energy atomic orbitals are called degenerated orbitals. For example, I am taking, these are the 3p orbitals. 3p orbitals. Okay, it is 3p orbitals. Next, let us take d orbitals. How many d orbitals are there in the d subshell? So d subshell contains 5d orbitals. D subshell contains 5d orbitals. 1, 2, 3 and 5. These are the 5d orbitals. These are all 5d orbitals. And f orbitals. How many f orbitals are there in the f subshell? F subshell contains 7 f orbitals. Okay, so these f orbitals are 1, 2, 3, 4, 5, 6 and 7. So these are all 7 f orbitals. F subshell contains 7 f orbitals. Now the orbitals possessing equal energy are called degenerated orbitals. What are they? Degenerated orbitals. Once again, what is mean by degenerated orbital? Degenerated orbitals, the orbitals with equal energy are called degenerated orbitals. Now we have how many degenerated p orbitals are there? So the degenerated p orbitals are 3, degenerated d orbitals are 5, degenerated f orbitals are 7. Okay, they are all having equal energy. The equal energy orbitals are called degenerated orbitals. Okay, now in this degenerated orbitals, how the pairing starts? So pairing starts with, in p orbitals, pairing starts with, okay, pairing of electron takes place when after all the degenerated orbitals filled with one electron each. Yes, all the degenerated orbitals filled with one electron each. Okay, then the pairing starts with fourth electron in p orbitals. Okay, in d orbitals, how it takes place? Yes, all the degenerated orbitals, all the 5 orbitals are filled with 1 electron each. They are all filled with 1 electron each of parallel spin. Then pairing starts with 6th electron. Okay. Next, in f orbitals, so all the degenerated orbitals filled with 1 electron each. Filled with 1 electron each. Filled with 1 electron each. Okay. All orbitals are filled with 1 electron each. So 7 orbitals and 7 electrons are filled like this. Then pairing starts with 8th electron. Okay, that is Hund's rule. Once again the statement of Hund's rule. Okay, it explains pairing of electrons. Fine. Pairing of electron takes place when all the degenerated orbitals filled with 1 electron each of parallel spin. All the degenerated orbitals are filled with 1 electron each. Okay, all the degenerated orbitals filled with 1 electron each of parallel spin. That means same spin. Okay, then the pairing electron takes place with anti-parallel spin. Okay, opposite spin. So in p orbitals, pairing starts with, in p orbital, pairing starts with 4th electron. In d orbitals, pairing starts with 6th electron. In f orbital, pairing starts with 8th electron. Because 7 orbitals are filled with parallel electrons, then 8th electron is starting pairing of the electron. Okay, that is the concept of Hund's rule of maximum multiplicity. Once again, so what is a clear statement of Hund's rule of maximum multiplicity? Pairing of electron takes place when all the degenerated orbitals are filled with 1 electron each of parallel spin. The pairing electron takes place with anti-parallel spin electron. Pairing starts with anti-parallel spin electron. Okay, in p orbitals, the 4th electron starts pairing. In d orbitals, 6th electron starts pairing, and in f orbitals, 8th electron starts pairing. Okay, last once again, the definition of the statement of this Hund's rule. Okay, the statement of the Hund's rule, it states that pairing of electron takes place only after all the degenerated orbitals filled with 1 electron each of parallel spin. Then the pairing takes place with anti-parallel spin electron. Okay, that is the statement of Hund's rule. Okay, now in p orbitals, 4th electron starts pairing. In d orbitals, 6th electron starts pairing. In f orbitals, 8th electron starts pairing. That is the concept of Hund's rule. Okay, so the concept of Hund's rule we explain in detail. Okay, then what is the significance of this rule? What is the significance of Hund's rule? Next, let us go for the significance of Hund's rule. Okay, what is meant by significance? Means what is the importance? What is the importance of Hund's rule? Okay, that is significance of Hund's rule. It explains, Hund's rule signifies to explain stability of atom or ion. Significance of the Hund's rule. Significance, or you can say importance of the Hund's rule. It explains stability of atom or ion. It explains stability of atom or ion. So what is the concept? How it explains the stability of atom or ion? Yes, the species means it may be atom or it may be ion. The species means it may be atom or ion. The species, atom or ion. The species containing half-filled orbital electron configurations. Half-filled orbital, half-filled orbital electron configurations, half-filled orbital electron configurations such as P3, D5, F7, half-filled orbital electron configurations, and completely filled orbital electron configurations, completely filled orbital electron configurations are extra stable. They are extra stable. What they said? They are extra stable configurations. Well, what is the main significance of this Hund's rule? Hund's rule signifies to explain stability of atom or ion. That is the main point. It explains stability of atom or ion. How? The species means it may be atom or it may be ion. Okay. The species containing half-filled orbital electron configuration like P3, D5, F7 or completely filled orbital electron configurations, such as p orbital is completely filled with 6 electrons, d orbitals are completely filled with 10 electrons, and f orbitals are completely filled with 14 electrons. Okay, so such configurations are extra stable according to the Hund's rule significance. Okay, that is a very, very important point we should remember. Okay, extra stable means what? The atom or ion is more stable. More stable means it is less reactive. The element, the species is less reactive. It may be atom or it may be ion. Okay, because of this stable configuration, we are saying that, so this is half-filled p orbital, that is half-filled orbitals, and completely filled orbitals are extra stable. So the species which contain the stable configurations are extra stable naturally. So more stable means they are less reactive. We can say that the species which contain such stable configurations are least reactive. Okay, least reactive. That means when it is least reactive, to remove the electron from this species is requires more energy. Therefore, that species possess higher ionization energy. Okay, so the species containing stable configurations, they are more stable. We can say that means they are extra stable configurations. They are extra stable because of their extra stability nature. They are less reactive. Okay, that is one point we understood. They are less reactive, no doubt. And so from the stable configuration, to remove the electron, we requires more energy naturally. So therefore, that species possess high ionization energies also. Okay, done. So stability of atoms or ions is completed. Okay, once again, what is the statement for this? Yes, species containing half-filled orbital electron configurations such as p orbitals are 3. The 3 p orbitals having half-filled, that means all the 3 p orbitals filled with 1 electron with parallel spin. Okay, so that is called half-filled p orbitals. Similarly, all the 5 d orbitals are filled with 1 electron. 1, 2, 3, 4 and 5. So all the d orbitals are filled with 1 electron each. Okay, so that is half-filled d orbital. Similarly, 7 f orbitals are filled with 1 electron each. Okay, that is called half-filled f orbitals. Okay, and completely filled p orbitals, that is all the 3 p orbitals are completely filled with 6 electrons. So that is p6. And the d orbitals, 5 d orbitals are completely filled with all 10 electrons. That is completely filled d orbitals. Yes. Half-filled orbitals and completely filled atomic orbitals configurations are extra stable according to the significance of the Hund's rule. Okay, yes. That is significance of Hund's rule is completed. That is, it explains stability of atom or ion. Let us take up, okay, let us take up some examples of that. Okay. Yes. So the species which contain half-filled orbital, the species which contain half-filled orbital. Example, let us discuss about nitrogen atomic number 7. So electron configuration 1s2, 2s2, 2p3. So p orbital is exactly half-filled. P orbital is exactly half-filled. And oxygen atomic number 8. So 1s2, 2s2, 2p4. Okay, so due to half-filled p orbital, nitrogen is more stable than oxygen atom. Okay, nitrogen is more stable than oxygen atom. So therefore nitrogen is less reactive than oxygen. Okay, because it is more stable due to half-filled p orbital, means it is less reactive. Okay, from the stable configuration, see, as we know that moving from left to right in the periodic table, you might have studied in the 10th class. So in a period, that is, let us take in second period, carbon, nitrogen, oxygen. Okay, so moving, just I am taking only 3 elements in the period. Okay, carbon atomic number 6, nitrogen 7, oxygen is 8. Moving from left to right, ionization energy should increase. Okay, so ionization energy should increase. That means according to the common trend, the ionization energy of the first ionization energy of oxygen supposed to be greater than nitrogen, but nitrogen ionization energy of nitrogen is greater than oxygen. You should remember this. Why? Because of the half-filled p orbitals of nitrogen. So because of the half-filled p orbitals, nitrogen acquires extra stability. Therefore, from the stable configuration to remove another electron, it requires more energy. Therefore, nitrogen is more stable than oxygen. Nitrogen possesses higher ionization energy than oxygen atom. Okay, that is a point we can understand. Next, the chemical inertness of noble gas elements. For example, neon atomic number 10. So configuration 1s2, 2s2, 2p6. The outermost shell, that is, the outermost shell contains s orbital and p orbitals. Okay, so all the s, that is s orbital and p orbitals, totally it is completely filled with all electrons. So because of the completely filled configurations, it acquires extra stability. So therefore, in every period the last element in which the complete valency shell is completely filled. Okay, all the orbitals belongs to that valency shell according to the Aufbau principle is completely filled. Therefore, because of this completely filled nature, so the atom is chemically inert. Okay, the chemical inertness of neon is due to completely filled orbitals. Okay, that is the point we have to understand that. So that is, all noble gas elements are they are inert due to completely filled valency orbitals. Okay, that is the point we understood. Next, coming to the special electron configuration of chromium and copper. Okay, chromium and copper, right? Let us discuss about chromium atomic number 24. Now this chromium and copper, they shows anomalous electron configuration. Okay, that is, we explained Hund's rule and we explained the significance also. What is the significance of the Hund's rule? Hund's rule signifies to explain the stability of atom or ion. That is, according to the concept of the Hund's rule, so the species containing half-filled orbital electron configurations and completely filled orbital electron configurations acquire extra stability. That is fine. Okay, now let us see the same the same concept is also applicable in other elements like chromium atomic number 24. Okay, the normal electron configuration of chromium becomes like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. It is a normal electron configuration. Okay, 4s2 and 3d4 normal electron configuration, we can write it like this. Okay, now according to the significance of the Hund's rule, half-filled d orbital is more stable. Half-filled d orbital is more stable. Yes, that is why. So now this is the 4s electrons like this. This is 4s2. Okay, and half-filled d orbitals are more stable. Okay, that we also understood. So half-filled d orbitals 1, 2, 3, 4, yes, these are the 5 d orbitals. Now the d subshell, all the d orbitals contain only 4 electrons. That is the normal electron configuration of the chromium atomic number 24. But in order to acquire extra stability, the 4s electrons excite, that is 4s electrons are transferred to the d orbital. 4s electrons are transferred to the d orbital to become half-filled stable configuration. Therefore, in order to explain stable configuration of chromium 24, we have to write 4s1 3d5. We should not write 4s2 3d4. Okay, always we have to write only the stable configuration. What is the stable configuration? 4s1 3d5. Why it should be 4s? Why it is 4s1 3d5? In order to acquire stable configuration according to the significance of the Hund's rule, so the atom should follow this configuration 4s1 3d5. Okay, so the half-filled d orbitals are extra stable. Therefore, chromium 24 shows anomalous electron configuration. Means deviation from the normal electron configuration. Okay, that is nothing but anomalous electron configuration. Why the element shows anomalous configuration? To acquire extra stability according to the significance of Hund's rule. Okay, so why? What is the reason? What is the special reason for this? So, okay, half-filled d orbitals are more stable. Why? If the atom is containing half-filled d orbital or completely filled d orbitals, why it should be more stable? That is a question immediately. Why it should be more stable? What is the reason behind it? Yes, the species which contain half-filled orbitals, they possess more exchange energy. It's a new concept again. Okay, so as the number of exchange pairs increases, the exchange energy also increases. The species possessing greater exchange, that is maximum exchange energy, and the species possessing minimum exchange energy are extra stable. Okay, maximum exchange energy and minimum exchange energy configurations are extra stable. That means 4s1 3d5 configuration. Let us see how it shows exchange energy. How many exchange pairs are possible? Let us work out on this. Okay, 4s1 3d5 configuration. How many exchange pairs are possible with this configuration? Let us see how many exchange pairs are possible. Number of exchange pairs. Let us work. Say this is electron 1, first electron. Okay, first electron, second electron, third electron. Okay, so let us mark like that. So now the exchange pairs. So that means this s electron can form can pair with the d electron, and this s electron can also pair with this. S electron can also pair with this. S electron can also pair with this, and this s electron can also pair with this. How many exchange pairs are possible with s electron? That is, the first electron can form exchange pairs with 1, 2, 3, 4, 5. 5 exchange pairs are possible in the first set. Next exchange pairs. Okay, this electron, second electron, can pair up with this 1, 2, 3, 4 exchange pairs are possible with that. With a second electron, 4 exchange pairs are possible. Next, with third electron, how many exchange pairs are possible? 1, 2, 3 exchange pairs are possible with this. With third electron, 3 exchange pairs are possible. Then, next, with fourth electron, let us see how many exchange pairs are possible with fourth electron. So this electron get paired with this, or this electron can pair up with this. So that is, fourth electron makes 2 exchange pairs, and the last fifth electron, how it makes exchange pair? The fifth electron can form exchange pair with this. So that is, fifth electron can make 1 exchange pair. So the total number of exchange pairs are, how many are there? 9. Okay, total they are 15 exchange pairs are possible. Okay, so total they are 15 exchange pairs are possible. So that is called, we can say 15E, that is exchange energy. Okay, so that is why half filled, that is 4s1 3d5, 4s1 3d5 electron configuration of chromium shows maximum number of exchange pairs and maximum number of exchange energy. Okay, maximum number of exchange pairs and maximum number of exchange energy. Therefore, so chromium 24 shows, chromium 24 shows, that is argon, means 18 electrons are covered. Then 4s1 3d5 configuration is extra stable configuration for the atom, chromium 24. You got it? Is it clear to all of you? So this is exchange pairs, that is why it is more stable. Half-filled d orbital is more stable. Why half-filled d orbital is more stable? This is the explanation for that. Why half-filled orbitals are more stable? That is the explanation covered in the textbooks. This concept is given at the end of the topic. Okay, so now it is explained along with this so that the student can understand much better. So why the d orbitals are more stable? Because of the more number of exchange pairs and more amount of exchange energy, it is more stable. Okay, similarly, okay, this point I think it is clearly understood. So now coming to the another element, copper 29. Copper 29. Copper 29. The electron configuration of copper is, okay, electron configuration of copper is, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. That is a normal configuration of copper. Okay, 4s2, 3d9, that is a normal configuration of copper. Okay, when it is a normal configuration, why we have to discuss it? So because to acquire extra stability, carbon shows deviation from the normal electron configuration to acquire extra stability. Yes, so that is 4s1, 4s2 and 3d9. That means all the 5 d orbitals are completely filled with 9 electrons. All the d orbitals are completely filled with 9 electrons. 1, 2, 3, 4 and 5. 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, all the 5 d orbitals are filled with 9 electrons. Okay, now to become more stable, still one more electron is required in the d orbitals. So therefore, the s electron is transferred from the 4s orbital to the d orbital. 4s orbital to the d orbital. Okay, so 4s orbital to the d orbital. Now the d orbital is completely filled. This configuration is 4s1 3d10. 4s1 3d10. So this configuration is extra stable configuration for copper 29. Okay, what is the electron configuration of copper? Atomic number 29. Always we should say, so that is outermost shell 4s1 3d10. Okay, 4s1 3d10. That is stable configuration of copper. It shows deviation from the normal configuration because of extra stability of copper. Okay, what is the stable configuration of copper? Always we have to remember, that is 4s1 3d10. Okay, that is extra stable configuration of copper. Why this configuration is more stable? So the d orbital is completely filled with 10 electrons. Therefore, according to the significance of the Hund's rule, so the completely filled d orbitals are more stable. That is why copper 29 also shows extra stable configuration. Okay, right. So one more element, the last element is palladium. Palladium atomic number is 46. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, then 5s2 4d 8 10 20 30 48. Yes, it is 48. There is 10 20 30 40 8 48. So this is the configuration of that element. So 4s2 3d8. So now in order to acquire extra stability, the complete s electrons are transferred into the 4d orbital. So therefore the stable configuration becomes 5s1 and 4d10. That is the stable configuration for that element. Okay, that is the point we have to remember. Okay, right. So the Hund's rule significance is totally, it is now completed. Thank you.